In this lecture, we look at solution of linear system of equations and Gauss elimination method. How to find the solution of system of linear equation using Gauss elimination method. So as you know, linear system of equations, a system of m linear equation in n unknowns is a collection of m equations, each of which involve n unknowns, right? Each only in the first degree. So the problem is to find a solution that satisfy all the equations simultaneously. So let us discuss a very simple case in 2 by 2 example. So two variables, two equations. So if you see in equation A, 2x plus y equal to 5, x plus 2y equal to 4. Similarly, you have system B and C. So let us talk about the first system. So if you look at uh, the first system, I will write it equation 1 and equation 2, and I multiply by non-zero constant 2 to the first equation, then it becomes 4x plus 2y equal to 10, which is your new third equation, and remaining the second equation as it is I have written. So now if you see in this second and third equation, the coefficient of y's are equal. So what we do is we are going to subtract equation 3 and equation 3 and equation 2. With the help of equation 2, I'm subtracting from equation 3. So which will give me x equal to 2 and y equal to, correspondingly we plug the value of y equal to 1. So this system gives me the unique solution x equal to 2, y equal to 1. Now one thing you notice here, so we understand from the above that the solution will not change if we do any of the following operation. So what we did, we multiply a non-zero constant, right? We multiply an equation by non-zero constant number, right? But solution does not change. Second property, add to an equation a non-zero constant times any other equation, right? Or in third, if you see, interchange any two equations. So if I perform these three operations, then solution for the given system is not going to be changed, right? So if you say in short, if I have any row Ri, right, I can multiply by a non-zero constant alpha, right, scalar, or you can say real number. So the second property, if you see, I'm going to multiply any non-zero constant alpha to any row I and add to another row, right? And third says interchange any rows, right? So these three operations are known as elementary row operations. Okay, so they are called elementary row operations, and these elementary row operations are reversible in the sense that if we apply finite number of elementary row operation to a system A and to get a system B, then system A can be obtained by applying the same number of elementary row operation to the system B in the reverse order, right? So what does it mean in the reverse order? This means that if we multiplied an equation, then by reverse order mean we should divide in the second case, right? So if you see, if you are having some matrix A, and if you are converting using elementary row operation to get another matrix B, then suppose if you have applied 2 times on R1, right, right, then in that case you have to divide 1 by 2 times of R1, right? So obtained A 2 times of R1, so whatever the row is, let's say 1 and 2, and then first row will be 1 2, then it becomes 2 4, right? Then if you divide 1 by 2, then you will get back your original matrix A. Okay, so this is the meaning in reverse order. And the equivalent system, right? What is an equivalent system of equations? So if we say that two systems are equivalent if they have same solution sets. So now if you see here, this A and B are equivalent because B is obtained after applying finite number of elementary row operation. The elementary row operation is this: multiply any row by a non-zero constant and multiply any row and add to a row, another row, and swap the rows, right? So three elementary row operations are important. So after applying finite number of elementary row operation on the equation will be equivalent. So you will get another system of equation which is called an equivalent, and then in that case both solutions are same. So the elementary row operation is useful when we are solving the system of equation using Gauss elimination method or Gauss-Jordan method or row reduced echelon form, okay, or echelon form, reducing the matrix into an echelon form. So now similarly we can find the solution for system B, and for system B if you see the solutions are like the same, and then we see in equation 2 and 3 both are almost just multiple of another equation. So first equation can be omitted, and then now we can plug the value of x in the second equation to get the value of y. So here y has multiple values because of the fact that x has multiple values. Then system has infinite solution. And then third system if we solve, then we can see that it is easy to see that the two equations are inconsistent and the system has no solution, right? So we can see in the picture wise. So first equation has solution as intersecting at single point. Second equation is overlapping on the first equation, right? So have multiple points are infinite solution, and third equation has no solution because they are not intersecting at any single point. Okay, so this situation is same for any number of linear equations in any number of unknowns, right? So now let us summarize first. The given system is either two category, consistent or inconsistent. Consistent means it has at least one solution. Inconsistent means no solution. So if solution exists, then again it becomes two cases. Either has unique solution or has infinite solution. Okay. So now let us understand the triangular system. So if I have a system a matrix A or system A, then we are trying to reduce into a triangular form. Triangular form means here elements are there, but below the triangle the elements are zero, right? So this is the way we are going to write the triangular system. So what had happened, below the triangle element, below the diagonal, all elements are zero. So this matrix is known as upper triangular matrix, right? So we reduce the given system into a triangular form, right? So if you see here the triangular form, the 0 times of x, the 0 times of x plus 0 times of y plus z. So this is a triangular form. If you see, it becomes 0 0 0 0 like that. Okay, so triangular form will help us in solving the system of equations using Gauss elimination method. Okay, so what it does, if you see here, it is very easy to solve, right? You can find z value from here, z equal to 3, and then you plug the value back. You plug the value z equal to 3 and get the value of y. Similarly, you plug the value back in this first equation to get the value of x, y, z. So now here, back substitution will work. Back substitution. Okay. So the whole idea is for Gauss elimination, reduce matrix into triangular form using using elementary row operation, right? And then and use back substitution, right? Use back substitution to get the solution. So now let us see in the last third equation z equal to 3, then second equation put the value of z, get y equal to 2, and then go to the first equation, put y and z value to get x. So and then what we have, so to solve the general system we apply the above elementary row operation to get an equivalent triangular system and then solve it using back substitution. This method is known as Gauss elimination method. So let us do one example. Consider the set of equations, and then to reduce this system into an equivalent triangular system, we first get rid of x from second equation, and then we get rid of x and y from the third equation, right? This idea we are going to use it here. Okay, so what happened? So we first get rid of x from the second equation and third equation as well. So first and second and third equation we want to remove the coefficient of x. Okay, so how to get the coefficient of x to be removed? Use the elementary row operation. So see, we do not touch the first equation. We multiply the first equation by a non-zero constant -3 and add to the second row. This is the second elementary row property, Rj plus alpha times of Ri. Alpha is non-zero, right? So here alpha equal to -3. So if I multiply by -3 to the first equation and add to the second equation here, so here operation will be R2 plus -3 times R1. This is the operation actually. Okay. And then when we add it, then we get rid of 0 here. X coefficient becomes 0. So we also multiply the first equation by non-zero constant 2 because we want to get rid of this value also. So if I multiply by first equation by 2 and add to it the third equation, then I will get rid of the x coefficient in the third equation, right? So my equation becomes now this. Now we won't touch equation 1, we won't touch equation 2, and we will touch equation 3 to get rid of y value, right? So how do we get rid of y value? We will get rid of y value after multiplying the second equation by -6 by 8 and add it to the third equation. So we will get the value of z. So now we have reduced into the triangular form, and then we can calculate the value of z first from the last equation, then go to the second equation, calculate the value of y, and go to the first equation, calculate the value of x. So now we got the value of x, y, z, right? Now we will do the problem in a shorter notation. Like if you see x plus y minus z equal to 9, 3 plus 11y plus 3z equal to 21, and minus 2x plus 4y minus 6z equal to 40. This is the operation we have used, right? And an equivalent system I have obtained, and then another one same operation we have used, and another equivalent system we have obtained, right? This means equivalent system, this symbol. Okay, now we will solve using back substitution to get the solution. Okay, back substitution I have already explained how do we solve. So we use the phrase system has been reduced to an equivalent system called echelon form. Okay, so now we will solve the same system of equations using echelon form process, like elimination process. Okay, so now we write in matrix 1 1 minus 1 the coefficient of the first equation, coefficient of the second equation, coefficient of the third equation, the third row of the matrix, and right hand side constant b 9 21 40. Then the same operation we have applied, R2 minus 3 times of R1 and R3 minus 2 times of R1. So what we will happen, we will be getting this two coefficient as 0. Okay, we are assuming that non-zero element and then making 0 to the below column. So this element is targeted as pivot element, pivot, pivot element, non-zero. Okay, so pivot element, below the pivot everything will be 0. Every member will be 0. Similarly, the first column is finished, then we will move to the second column with lower row. So pivot element will be now 8. So we will make it 0 below the pivot element. Okay, using this operation. So next matrix becomes this. So this system has been reduced to the triangular form. We will write back into the equation x plus y plus x plus y minus z equal to 9, 8x plus 6y equal to minus 6, and so on. And then we use the back substitution as before to get the same solution. So now we will talk about the general system of linear equations. So system of M linear equations and unknowns is of the form a11 x1, a12 x2 plus and so on a1n x1 xn equal to b1. Similarly a1 amn am1 x1 and so on amn xn equal to bm. Okay, so now if we want to know the solution, then it will be formed n tuples, okay, which satisfy the above equation. So system in the matrix form, let A can be written as A11, A12, A1n and so on, all the numbers of the coefficient of the matrix. This is called coefficient matrix. We represent as A. So each coefficient is being written as an element, and X is the solution. X1, X2, Xn is a column vector. B1, B2, Bm is the column vector, right? So now, which is equivalent to solving a system and can be written as Ax equal to B, right? And A is rightly called the coefficient matrix, and B on the RHS is called the coefficient of the right hand side. Okay, then what we have to do, we have to write the A augmented matrix B, A augmented B. We write A slash B. Sometimes we also use the bar line. Okay, so now this notation is called augmented matrix of the system, right? And how to find augmented matrix? A coefficient matrix, and the next column I will plug as it is just from the P coefficient to form the augmented matrix. Now matrix in echelon form. A matrix is said to be in echelon form if all zero rows occurs below the non-zero rows, right? So if you have a matrix like this 0 0 2 0, so I want to convert into echelon form, I can write 2 0 0 0. What I did, I applied elementary row operation R2 to R1, right? Because all zero rows occurs below the non-zero rows. So in this case, zero rows are above the non-zero rows. But what it says, zero rows occurs below the non-zero rows. So non-zero rows, now this is a non-zero rows and all zeros are below the non-zero rows. Okay. And let if I and k, if the first non-zero entry pivot of row I occur in the ji column and then first non-zero entry of the row k occurs in the column jk, then ij is less than or equal to jk. So what does it mean? So if you see all the entries below the pivot entry in the column in which the pivot resides are 0. So now if you see it here, this I and j, if you see I less than k, first non-zero entries. So if you see, this is the first non-zero entries, right? So this is your I, and then k, somewhere k will be here, and so on. So I less than k. See, I is less than k, right? 1, I is 1, first row, and k is second row, right? So first non-zero entries of the pivot occurs in the jth column. So j, suppose you say j, and this is ji, jk, right? So ji, jk, if you see, ji is less than jk, second column, first row, first column, right? So if you see it here, uh, the all the entries below the pivot entry, right, in the column which are the pivot resides are 0. So if you see that all the entries below the pivot, this is my pivot element, all the entries are 0. Next pivot element, all entries are 0, right? Next pivot element, all entries are 0. So it will form a staircase type, right? So this is the next row, next column, there is zero elements. Then we will look any non-zero entries. If no non-zero entries, then we will move to the next row and next column and the same row and find 6 here as non-zero entry. Okay. In a similar fashion, we will be getting these all are the echelon form matrix. Okay. Thus now we apply the elementary row operation to the augmented matrix and reduce the matrix into echelon form, right? Triangular type form, if see, right? Which is known as the equivalent of system. So now let us solve the system by reducing echelon form. So first this equation, second equation, third equation. So now first equation, I will write the augmented matrix A augmented B, A augmented B. So what will happen? First non-zero entry 4. This is called pivot. Then I have to make it 0, 0 below the pivot entry, right? To make it 0 below the pivot entry, what operation I need to perform? R2 minus 5 by 4 times of R1 and R3 plus 9 by 4 R1, right? So I will have the zeros here. Similarly, the operation applied on the each row as usual. So we are going to get the rows are like this. Now we move to the next row and next column and below row. Below row is this element. This element is itself non-zero. So we have to just add this element to get the 0 below column, right? Below the pivot entry. So when we add this, what we are going to get it here, after adding this, I'm going to get it here 0, right? So now this matrix is reduced in echelon form. Now solve, we have to solve, we find the solution. So if you see here, the last equation, something left hand side is 0 and right hand side is 11, right? So what does it mean? The system is not having any solution, and which is called an inconsistent. This system is inconsistent because if you see, 0 times of x plus 0 times of y plus 0 times of z is equal to 0, equal to right hand side 11. So 0 cannot be equal to 11. Hence, this system is inconsistent. Okay. Now we will solve another system. Solve the system by reducing it to echelon form. So solving this system will make 2x plus y plus 2z equal to 1, x plus y equal to 0, x minus 2y plus 6z equal to 3, and x minus 2z equal to 1. So now the same argument, make a pivot element non-zero and then make 0 to below entries of the same column using suitable elementary row operation. So here 1 by 2 times of R1. If I do 1 by 2 times of R1, then it becomes 1, right? And then subtract it from R1, R2, R2, R3, R4, right? Same operation. So I got 0, 0, 0. Similarly, we move to the next column and below row. So 1 by 2. 1 by 2 is non-zero. Then we have to make it 0 to the below entries. Okay. And using suitable elementary row operation. Okay. Then we got 0, 0. And then we move to the third column below row. So third column below row. But you know in echelon form, all the zero rows are below the non-zero rows. So non-zero rows is the fourth row. So we interchange it, right? Once we interchange it, we got non-zero element like this. Okay. And then already this pivot entry zeros is already there. So now system is reduced to echelon form. And then now we are going to make x into 0, y into 0, z into 0 equal to 0. So 0 equal to 0 is true, right? Here 0 equal to 0 is true. Then the given system is reduced to echelon form. And then now from third equation 0 plus minus 4z equal to 0. So which implies z equal to 0. Once z equal to 0, you have to plug into the first equation. So you will get y value and similarly you will get x value. So this system is having unique solution, right? And let us solve one more problem. Solve the system of equation by reducing it to echelon form. So this is the system. Now you can find the argument pivot element, make it 0 by elementary row operation, and then I got an to this value, and then again make it 0 by this, then we will get the RHS value, and then system is reduced to echelon form, and then find the solution by putting the value of variables. So you will get this variable. Okay. So for this, you see below 0, 0, 0, all are 0. So here z equal to, if you see 0, 0, 0 equal to 0. So 0 equal to 0. Now you have to solve second equation. Second equation will be, these two equation will be, so you have to solve the y in terms of z. So z is here free variable. Because why it is free variable is if any one of the column is not having pivot, the column which are not having pivot in the echelon form is assumed to be free variable in that system. So this is z is not having any pivot entry. So z is free variable. Z can take any value, whatever z wants. Okay. Now, so we solve y in terms of z, and then similarly x in terms of y, and since y is already dependent on z, so all x and y depends on z value. So now z is called as free variable because z variable does not have any non-zero pivot entry. Okay. Hence we can write that x in terms of z, y in terms of z, where z is free variable. So now you choose any z variable and then you plug into it any z variable. This is the general solution. And now if you choose a particular solution, let's say z equal to 0, you plug 0, 0, 0. So 14 by 17, 12 by 17 and 0 is one solution. You can also find many solution as you want. Okay. So this is what I can say. And then now you